So we have found the f. We are in step 2.5. We use step 2, and then step 2 is finding using the boundary condition. So I've used the boundary condition. Why I say 1/2? Because we go a little bit forward in the sense that from here we actually gone through, and we now know that your P must take this form already. Right? Your P take this form. P take this form also means K take this form. Right? So maybe we want to write down, actually this also implies my K has to be what? Negative P square, you know. Right? So that means my K has to be negative n pi on L square. Right? Remember this, why? Because now we're going to do the other equation, the other ODE, and we're going to apply the initial condition. That is step 3. Step 3. So let me draw a line first, which means that we have to look back at what was it just now? We had G dot C square G, right, equals to K, right? K, right? But K is negative P square. I don't want to write this big thing. Let me just use negative P square. So equals to negative P square, right? So let's do some simplification. So I have G dot here. Then what would it be? It will be plus C square P square G equals to 0. That is my second equation. And if you solve this, actually it will be better, maybe better if you write it down as G dot equals to negative C square P square G. This is like your dy dx equals to something y. What's the solution? Write down the solution. G equals to some constant A, B, C. Okay, C, capital C. Okay, times e to the negative C square, small c, P square T. Agree? Not very troublesome. Why I say troublesome? It's because your P is not just any P, right? Your P must be n pi over L. So actually your P, strictly speaking, depends on this number n. So let me rewrite this guy. Okay, C square P square let, so if I say let lambda to be equals to C times P, okay, C times P, so I get rid of this. But then because there's an n here, there will be a number of lambdas, lambda n, right? So let lambda n be C n pi over L, so that I can replace this G of T to be equals to some constant multiplied by e to the negative lambda n square T. Correct? Can you check and see if I'm correct? Correct? So, but then for each lambda n, you get a different coefficient. So I put C sub n. And for each one of these one is different, you will have Gn. Right? Because all these are related. If I say that this P has to depend on n, then this B will depend on n, which means that F will depend on n, which means that your lambda will depend on n, which means that your C will depend on n, which means that G will depend on n. So you actually don't have just one solution, you have many solutions for F. You don't have just one solution for G, you have many solutions for G. Did I say we have solution for G? I did, right? G. So we're done. in a sense, because what did we say we want to find? F and G, right? We found F and G, but we found many F's and many G's, right? So what exactly, how can we then say now we want to construct the solution? What do you think? You see, for one n value, let's say n is equals to 1, I have a f1 and I have a g1. My solution is actually f times g. So I will have f1 times g1. So that's one solution. So that's actually my u sub 1. Then when n is equals to 2, I have another f2 and a g2. I multiply them together, I have a u2. Is u1 a solution? Yes. Is u2 a solution? Yes. So what would be, and then I have many, right? I have so many because n is any integer. So I have infinite number, and I will multiply, I have infinite number. So what exactly is the solution? If I have so many of these u1, u2, u3 and so on, so the general solution would be the sum of everything. Because you remember what we learned about solutions, general solutions, linear combination would be a solution. Right? Same thing here. So in other words, if I write down un of xt will have to be fn of x times gn of t. Okay? Then it follows that this is equals to, what is fn of t is now bn star, you will find out why I need a star, sine n pi on lx multiplied by cn e to the negative lambda squared t, like this. So this is my unxt. But I say this is just one u1, u2, u3, just that formula, just that expression. If we want to construct the actual general solution, we need to sum all the individual solutions, which means that we can write down now. Therefore, the solution is, so by the way, that is my step 3 to find this. I applied the initial condition. So now I want to construct the solution. The solution will be uxt. Now it's uxt, not un anymore. It's the sum of all the possible products, of f and g. So that would be going from n equals 1 to infinity of now if I take this times this, I can get bn star times cn. Let's just call that product to be bn. That's why I have a star just now, so that I can now use bn and sine n pi over lx times e. So I don't have any more cn because cn times bn star is just my bn. Okay, just this one. Okay, e to the negative lambda n square t, where lambda n is equals to cn pi on l. By the way, this is just constructing it. Haven't quite finished. I said we apply initial condition. Actually, we have not. We only have constructed or found a form for the G. We apply initial condition. Okay. Now we apply initial condition so that we know what to do with this Bn, because there's still this Bn lying around, right? So we apply the initial condition. What's the initial condition? U x 0 equals to f of x. Right? That's the initial condition, right? So let's apply this initial condition. Okay, u x0 equals to f of x to this thing. What do? Left hand side, substitute t equals to 0, left hand side becomes fx, right? Right hand side, substitute t equals to 0, what do you get? Can become 1, right? Substitute t equals 0, this one becomes 1. And what do you get here? Sum n equal 1 to infinity bn sine n pi on Lx. Am I done? What was my objective just now when I said I need to apply? I say I need to apply the initial condition so that I can find Bn. So when I apply the initial condition, I get this, right? Can I find Bn? Can I find Bn? What do you think? Can. Why? Why? Because this form on the right hand side is simply the Fourier sine series, a Fourier series of f of x. Right? This is the Fourier sine series for f of x, which means that if this is going to be the Fourier sine series of f of x, then I can write down Bn, and I use the formula that we have earlier on, 2 over L integral 0 to L of f of x times sine n pi over L of x dx. Done. Finished. So in other words, the solution of I got to go back all the way, I don't know how many pages. Where? Here. The solution of this problem, subject to the initial, subject to the, the solution of this problem subject to this initial condition and this boundary condition. Be careful, is this boundary condition and this initial condition. This solution of this problem, or this partial differential equation, is this. This is the solution. So this solution is a series, right? So everything is known except that your Bn has to be found. Your Bn is simply 2 over L integral 0 to L fx sine n pi L x dx. That's all. Okay. So if you are given that particular problem, you will have to be given the value of L, right? 0 to 1. Let's say if L is 1. And then you will have to be given f of x, right? Say f of x is some function. Okay? Then given those knowns, everything is known because you can, in principle, everything is known because you know L, well, you know f of x, you know L, this is just a integer, n is an integer, so you can integrate this. When n is 1, you put 1 here, so you find B1. When n is 2, you put 2 here, you can find B2. You can find all that in principle, I'm saying in principle. You can find until infinity. Then you put all this inside here. And then you can sum. Okay, so everything is known, right? Everything is known already. So this is the solution. A bit troublesome, a bit long, but this is the solution. Okay, so we will look at an example to see how we apply this solution. Okay, so example 4. Find the solution of the heat equation given by equation 6 in the notes, subject to 7 and 8. One is boundary condition and one is the initial condition. If your f of x, okay, so now example 4. You are given the f of x, that means that is the initial condition, is the distribution of the heat at t equals to 0. F of x is the distribution of the heat at t is equals to 0. Now is given as 3 sine 4 pi x over L. In this particular case, the L itself is general, is not known. But we know that if your L is given, then we know that f of x is a certain function, and the heat is distributed over L from 0 to L in this manner, meaning that from 0 to L you have a sine function, right? So the heat is cold, hot, and things like that, right? Across the length from 0 to L. That's the initial, that's the starting point. So the question is that as time goes on, as t goes on, and what would be the u at different position? In other words, what is u at t? So from our solution straight away, we can write down the solution is this. Okay, I can write down because the conditions are the same. So the solution is this, where now your f of x is this, and this is how we will find, but it's a bit troublesome. So that is a little bit of shortcut in this particular problem, because we're not going to perform the integration in this case. Okay, we just use this. So we will say that u at x0 is equals to f of x, right? And we know that that is equals to sum n equals to 1 to infinity of bn sine n pi on Lx. Right? I'm just quoting directly from here. Okay? Okay? By right, I should go there and then go and integrate. But then in this particular case, because my fx is quite special, okay, that means my fx, based on this, my fx should be equals to, based on this, b1 sine pi on Lx plus b2 sine 2 pi on Lx plus b3 sine 3 pi on Lx plus b4 sine 4 pi on Lx plus b5, I don't know how far I should go, but can you see something? Stop me, otherwise I will continue. Okay, can you see something? And this is supposed to be equals to what? And this is supposed to be equals to 3. Okay, when we do the integration, what are we trying to find? b1, b2, b3, b4, b5, b6, and so on, right? So now I put this to you. I give you this particular equation. The one in green equals to the one in black. If you can't see which is green, which is black, this is green, this is black. So you have this one equals to this. And I ask you, what is b1? Good. What is b2? What is b3? What is b4? Don't tell me 0, 3. Okay? And the rest? So if I choose b4. If I choose b4 to be 3 and the rest to be 0, have I satisfied the condition? Have I found all the b's that I want to find? Okay, so that's all. So all I need to say is that from here, by observation, we choose b4 to be equals to 3, and the rest of the b's, b1, b2, B3 skip 4, B5, B6, and so on to be 0. Okay, to be equals to 0. Then we can write down my UXT. And my UXT is supposed to be sum over all n going from 1 to infinity of Bn sine n pi on L x e to the negative lambda n squared t. Okay. To sum everything is 0 except B4. Right? So this means that my solution UXT is 3 sine, I only have a B4, 4 pi over L x times e to the negative lambda square here will be C n pi over L, right? C n pi. So n is 4, C pi over L square. This over L square times t. So this is my solution. This is my this is my solution to the problem. So if you don't believe me, how do you check? Differentiate it once with respect to x, differentiate it twice with respect to x. That gives you the 2u by dx squared. Differentiate it once with respect to t, that gives you du dt. Put that inside the heat equation. Left hand side equal right hand side. That's one way to have. But you also have to put down u at 0t, one endpoint. U at 0t must be equal to 0. Do you think it's equal to 0? Yeah, because you get a sine 0, right? U at lt, put x equals to L, you get a sine 4 pi, 0, that goes off. U at x 0, initial condition. At 0, this one goes off. What do you get? F of x. T0, T0, this goes off. You get this, right? Boundary condition, initial condition satisfied. You take this, you differentiate twice with respect to x, differentiate one time with respect to t. You can check that it's satisfy the heat equation. Solved. Okay. Example 5. Okay, solve the heat equation 6 subject to 8 and 7 if now we have fx equals to 100, you get given L and you're given C square. Okay, so I'm going to straight away write down what is the Bn. The Bn will be 2 over L, L is pi, then you have integral from 0 to pi, okay, 0 to L, multiply by then f of x. In this case, f of x is just a constant, 100, right? And then sine n pi on L, L is what? L is pi, n pi on pi times x dx. Okay, this is your Fourier coefficient, right? Right? Why is it Fourier coefficient? Because when we found our f of x is a Fourier series, where your Bn is defined by this. Okay, and let's perform this integration. You get 200 over pi. Let's take out the constant, and then you will have integral 0 to pi of sine, the pi cancel sine nx dx, right? This looks very familiar. I think we have done this before. Of course, your n is 1, 2, and so on, positive integers. And then, okay, let me very quickly write down. This will be 200 over pi. And then you have negative cos nx on n evaluated between 0 and pi. we can write it in the form of what we had before, or we can split it as a two parts. One is when n is odd, and one is when n is even. So we will have negative 1 minus 1, like that, over n, for n is odd, or 200 over pi, and negative of 1 minus 1 over n, okay, for n is even. Okay. Maybe I think we have done this earlier, right? I think this one was 1 minus, you can just write it down this way lah. I think this is neater. Okay, maybe forget about this part. So forget about this odd and even. Just this will do, because that will take care of the odd and even cases. Okay, so this is our Bn. So in other words, you have to write down uxt, because that's our solution. This is not our, this is only part of the solution, finding the coefficient. So your uxt in this case, can you write down? So we take out the constant, because we have a sum, so we take out the constant, then we sum, and you sum n from 1 to infinity of Bn. Part of the Bn has been taken out of the sum, and then we have sine n pi x over L. L is pi. N pi x over L. So the pi, so sine nx, right? And then e to the, so because this is just Bn sine n pi x over L, and b to the negative lambda n square times t. Lambda is c n pi over L. C is 1. So n pi over pi is just n. So negative n square. Okay, so this is the solution now. The solution is an infinite sum in this particular case. Okay, you want to see how the solution looks like? Okay, let's call our friend up again. Now you know why it is so useful to learn MATLAB. Okay, I hope this is correct. Yeah, it's written a long time ago, but it's still relevant. What I do in this particular case, okay, take you through this little program first. So first I have the values of x, and at different time, because you see now we want to find the solution in the form of a distribution of the heat, right? So at time t equals to 0, that means our initial condition, if you look at what is given at time, the initial condition at time t is equals to 0, you have fx, right? Fx, right? Is 100, right? This is my initial condition. Sounds a bit funny, initial condition. Actually, it means that it's a distribution of the heat at time t equals to 0. So what does that mean? It's 100 throughout, uniform. But a bit funny because at the end is 0. Remember the two boundary conditions. So in other words, if I were to plot x versus u, at 0 is always 0 because that's a boundary condition, cannot change over time, boundary condition. And at pi, x equals to pi, right, because that's the whole length. It's very hard to find a rod which is pi in length, but let's imagine we can. Okay, So at these 2 points is 0. That's initial condition, as well as boundary condition, forever it will be there. Then at time t is equals to 0, inside, okay, inside is at 100. So there's a bit of physical impossibility there, because from 0 suddenly jump to 100, we know physically it's not possible. Okay, but in mathematics you can do anything. So it's 100 all the way here. So as time goes on, what do you think will happen? The two boundaries are kept at 0, two ends of the rod kept at 0, inside all very hot, 100 say degrees Celsius. Okay, as time goes on, what do you expect will happen? The two endpoints cannot change. Okay, the two endpoints will always be 0. So it cannot heat up, the endpoints cannot heat up. For some reason, you put something there to maintain it at 0. But the inside starts at 100. Over time, it will cool down. So what do you expect? Where would you expect to cool down faster? Near the ends or near the middle? Near the ends, right? Because it's nearer to the 0. So over time, what do you expect? Can you think you draw some graph in the air to show me what do you expect? Right? So possibly at first it is like this, then after a while it's like that, then like that. This is what we would expect, right? Does it make sense? Does it make sense? Because it has to be at 0 at the two ends. You can't change that. That's a boundary condition. So our thing is supposed to do that. So if I run this, it shows me the first one, and then the crosshair actually let me label it. I will give you this program. Okay, these are my. Can you see? So this is what we will expect, and I program. I basically write the solution in the form of a program, and this is what we get. So the solution works. Unfortunately, the solution is so complex, right? And this is for a very simple case. This is a simple case, right? And we have such a imagine if you have a more complex PDE and a more complex situation with a very different boundary conditions and so on. You're going to go through a whole analysis and go through an integration. In the end, you still find a series as a solution. Not worth the trouble, right? Because if I find a series, I find this series, right? It's sum from n equals to 1 to infinity, bn, blah, 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 and so on, right? Can I? It will be exact. It's exactly equal, but I need to sum to infinity for it to be exact. In practice, I cannot sum to infinity. I have to stop somewhere. As long as I stop somewhere, it's an approximation. So I still find an approximation even though I have an exact answer. So why don't I just approximate right from beginning? And that's what we're going to do next week.